This lesson is on special factoring. The factoring here is special because we're looking for recurring patterns that come up over and over again, which we can use to our advantage. So let's begin by looking at some common formats and developing some formulas to use in the future. The first of which is the difference of squares. You may have seen this before, and you may have also remembered that there seems to be something interesting that always happens when you multiply two binomials together when they have the same first term and last term but different signs. Well, let's see what happens. A times a gives us a squared. A times negative b gives us negative ab. Positive b times positive a gives us positive ab. And the last term is negative b squared. So what is so interesting about this? Take a look at the middle two terms. You'll notice because of this plus minus thing here, your middle terms are always going to cancel. So that leaves you with a squared minus b squared. Therefore, whenever you see, and let's write this in a different color, a squared minus b squared, you can refer to the factored form as the a's in the first terms, the b's in the last terms, so the roots of these items, and a plus and a minus. Let's continue to the next one, the perfect square trinomial. So it's essentially the same thing, a and b, but both signs are going to be the same. Notice I've written plus minus in this fashion. We could have written it as two separate formulas, but I'd like you to see how this works. So this works as if, okay, if this was a plus, everything on the top row will be written with what happens to that plus, and if this was a minus, then the corresponding signs will be written in the bottom of the signs. So let's check it out. Squaring means bracket times itself, so it'd be like this. First times first gives us a squared. A times plus or minus b is going to leave us with plus or minus ab. Plus or minus b times a gives us plus or minus ab again. So notice if this one was a plus, then both of these would be plus, then these would both be plus. If this one was a minus, then both of these would be minus, and both of these would be minus. And the last term, if you multiply positive b times positive b, you'd get positive b squared. If you multiplied negative b times negative b, you'd also get positive b squared. And this simplifies to giving us a squared doubling the middle term. That's why this one is so interesting. And it doubles to either a plus if this was a plus or a minus if this was a minus, 2ab plus b squared. So our formula here can be expressed with any time we see this format with two squares for the first term and the last term. They are perfect squares, and the middle term is plus or minus twice the first times the last. Then we will know that it is a perfect square trinomial format. Notice that this is a trinomial, and we do have a way of factoring the trinomial through decomposition. However, if you notice that they're perfect squares, it might be easier and quicker to just get to this right away. Alright, let's take a look at the last one here. It has to do with cubes, so you may not have seen this one yet, but let's check out these instances where you'll notice that you're left with cubes. So let's multiply this out. A times a squared is a cubed. A times negative ab is negative a squared b. A times positive b squared is positive ab squared. And so on. Multiply all of them by b, you get plus a squared b. And notice I'm always leaving them in alphabetical order so that I can notice any like terms if they're existent. B times negative AB is negative AB squared, and B times B squared is positive B cubed. Let's take a look at all these middle terms. We've got a negative A squared B and a positive A squared B, a positive AB squared and a negative AB squared. So this here has been tailored so that all the middle terms cancel out, leaving us with a sum of cubes. Therefore, we can use the following. If you see something of the format a cubed plus b cubed, that gives you the following expansion. A plus b times a squared minus ab plus b squared. So this is a formula that would be on your formula sheet. It is a pre-prepared multiplication of polynomials that leads you with this interesting result. Okay, let's go with the next one. So in red here, we're going to multiply all the terms by a and then all the terms by negative b and see if something happens differently this time. So multiplying everything by a gives us a cubed plus a squared b plus ab squared. Multiplying everything by negative b is going to give us negative a squared b, negative ab squared, and negative b cubed. Let's see if the middle terms cancel out. Positive a squared b minus a squared b, gone. ab squared minus ab squared, hey, look at that, they're gone. So a cubed minus b cubed is the result of that. So this is a difference of cubes. So if you had a minus here, how would that change the following signs? You'd have a minus b and a squared plus ab plus b squared. So there you go. These are the three main special formulas to look out for. So let's take a look at some difference of squares examples. Bam! There's our difference of squares formula. Let's see if we can use it. So sometimes it's nice to rewrite it in the format so that it looks a little more the same. So what squared minus what squared is x squared minus 16? This is x squared minus 4 squared, meaning we're going to have x, x, and 4 and 4, which gives us x plus 4 times x minus 4, done. We didn't even need to do anything. However, you may notice that if you want to back up, you could write this as x squared plus 0x minus 16. You could find a product and a sum and so on, and you would get to this. So you can try that if you'd like to convince yourself. Another way to check is to multiply this out, and you'll notice your middle terms cancel and you're back to the expanded form. So here we got some bigger numbers. So all we need to do is notice we have two terms. They're both perfect squares. This one's 5a all squared and this one is 8b all squared. That leaves us with a difference of squares. 5a plus 8b, 5a minus 8b. You can also continue with things like x to the power of 4. What squared minus what squared is this? And if you're not sure if something's a perfect square, you can always use the square root button to find out. So 625, what's the square root of 625? It's 25, meaning 25 times 25 gives us 625. Okay, now x to the power of 4, remember to get that, you would have to take x to the power 2 to the power of 2, because 2 times 2 gives us 4. Okay, so that tells us that that is x squared minus 25 times x squared plus 25. And notice I can write plus or minus in either way. Here, I'll keep it with the way this formula is written in this case. Now, you think you're done, but always look at both your brackets and see if they can factor further. Don't we have another difference of squares here? Isn't this x squared minus 5 squared? Yes, it is. So keep going if you can. Always factor as completely as possible. Using the difference of squares formula again, you get that. Notice it doesn't work for plus. You can try and justify that for yourself, or you can ask in class. Okay, next up, let's see if we can factor this. It doesn't seem we have nice perfect squares, does it? However, we have two terms. So all we can really do is take out the greatest common factor. What is the greatest common factor of 20 and 125? Well, 125 is divisible by 5 and so is 20. So let's try that. Let's take out a 5, and we cannot take out any x's, but we can take out a y. And then we're left with 4x to the 4 minus 125 divided by 5 gives us 25. Oh, look, those are now perfect squares. And we're left with a y squared. Nice. So now because we have two terms that are perfect squares, we can relate them to the difference of squares formula. So that's 5y, two brackets with a plus and a minus, and you're taking the root of both items. So that'll be 2x squared plus 5y, and 2x squared minus 5y. Notice that if this here 5y was a nice perfect square, you could keep going. However, it's not, so we can't keep going because it won't be factored over the integers any longer then. So that is all we can do in that case. Let's move on and look at some perfect square trinomial examples. So all of these are in the format of the perfect square trinomial, where you have a bracket squared giving you a trinomial. So the first and the last terms are perfect squares. So that's what you're looking for. But then you gotta check the middle term. You want to make sure that the middle term meets up and is actually indeed twice the first times the last. So you almost want to just write it in that format and see if you can make it work. So what square and what square would be at the ends? That'll help you find out what your a and b is. So here we have x and here we have 7. So our middle term should be, in this case, negative twice the first times the last. Now, does that work? Is this equal to negative 14x? Yes, it is. So you've checked the middle term. Great. Therefore, you can just write it back into the perfect square. So since this is a minus, we're going to have a minus, and we basically take the first and the last terms that are squared and put them in. You could also just take the first and the last, take their roots, put them in with the sign, and then on the side, open it up by distribution and just double check if your middle term works. If your middle term doesn't work, then you can't use the trinomial formula. So sometimes that will happen, so make sure to check your middle term. Alright, let's try the next one. This looks like we have a perfect square at the beginning and the end. So let's just look at those. That would be 4a squared, and this would be b squared. So it should give us 4a, and the middle term there is a positive 4a plus b squared. It should be this answer, but let's just check the middle term. If you multiplied all this out, you'd notice that the middle term would be double the first times the last. If you don't like this way, you can take this and expand it completely and check the middle term that way as well. But yes, this is 8ab, so therefore that is correct. The next one here looks a little more complicated. So it almost looks like there should be something we could fix in here to make it look a little nicer. So always, always, always when you're factoring, you always want to take out the greatest common factor first. Let's try and do that. Is there a greatest common factor here? Well, these divide by 3, by 5, by 3. No, there's nothing in the numbers. However, the minus sign should come out. And how about the letters? I think we have a factor of x that could come out. And that's about it. So let's try that. Let's take out the negative. The negative comes out. And the x comes out, and we're left with 9x squared y squared minus 30xy plus 25, and the x came out. That's it. Okay, so let's try this. Is the first term and the last term a perfect square? Yes, they are. So this guy has to stay. Okay, so the first term, to make that a square, you'd have to have 3xy. 3xy times 3xy gives you 9x squared y squared. And the last term would have to be 5 squared. Notice this is a higher level question, so it is a little more difficult. But see if you can follow the format and finish it off. Okay, now let's check the middle term. The middle term should be minus twice the first times the last. Let's see if our first times our last gives us our middle term. 2 times 3 times 5 is 6 times 5 is 30. xy, it is. Hey, look at that. So what this allows us to do is keep the outside common factor out, and we can take the first and the last because of this formula, 3xy and 5, and the minus sign all squared, and this should work. If you're not sure, you can open it up, distribute it, and see if it comes back to this. Remember to multiply only 2 at a time and keep them in brackets as you do so. Now let's take a look at sum and difference of cubes examples. So we got this fine formula here. You'll notice when you have two terms and they can be written as cubes, we can follow this format and expand in that way. So are these perfect cubes? Why, yes they are. X cubed plus 1 cubed. So our a is our x and our b is our 1, and we're filling in the formula in our a's and b's as so. So you can basically, you will have this formula given. You're taking the plus version, which is all the top signs if there are 2. So that gives you bracket times bracket, the first plus the last, and then the first squared. You could open little brackets for yourself if you'd like, minus the first times the last, x times 1, and plus the last squared. These are simple, so I'm not putting little brackets, but you could be going like this and just inputting the numbers. So that simplifies to give you x plus 1 times x squared minus x plus 1. If you're doubting that this will multiply out to give you back this again, you can try it on your own and distribute and see if it works. This next one here, 8 can be written as 2 cubed, and n is already as n cubed. So notice you could either do it this way, or you could rewrite this as negative n cubed minus or plus 2 cubed, and factor out the negative so that you have your n cubed going first. Sometimes in the future, applications of factoring, it is useful to have your variables at the beginning so that you're able to see if it cancels with any other similar brackets. And you'll see that a bit later. So let's keep it this way. So negative stays outside, and we're going to have the negative version, which is the bottom row. So that's going to be a minus b, and then a squared plus ab plus b squared, and our a is our n, and our b is our 2. A is n, a is n, b is 2, b is 2. So you're just inputting the formula that we've created in the past. And that's negative n minus 2 times n squared plus 2n plus 4. Last one here. Here we've got 64a cubed and 27b cubed. So because we see the cubes, there's no greatest common factor to take out. Let's just see if we can take the cube root of 64. So that is 4. So that's 4 cubed gives us 64, 4a in a cubed. And 27 is 3 cubed, 3b to the power of 3. All right. Now, again, just as before, we're sticking it into the formula with the negative there. So let's try that again. That's going to be a minus b and a squared plus ab plus b squared. Our a term is 4a, and that goes into wherever a was listed in the formula. And our b was 3b, just inputting that in there. Now let's simplify that. That gives us 4a minus 3b. And remember, this is why I'm writing the brackets, because we're taking 4a and squaring it, not just a and squaring it. So that'll be 16a squared plus 12ab plus 9b squared. And if you'd like, you can multiply that out and you should get this difference of cubes back again. The last example here is a bit of a word problem. They're telling us that the circular dartboard has a series of rings and a solid center. The solid center is called the bullseye. So they've written a formula for us that represents the area of the outer black ring, and it's pi times big R squared minus pi times little r squared. And you can almost see where that formula comes from. Big area minus little area gives you the outer component. They want us to factor this primarily because they probably want a simpler formula to input, maybe into a calculator or something that's a little easier to understand with less squaring going on. So let's take a look if we can factor this. There's a common factor of pi, so let's take that out. And then we have big R squared minus little r squared. Hey, that's a difference of squares. So pi stays, and difference of squares has plus and a minus, r plus r, r minus r. So if someone doesn't know how to square things, you can just tell them, well, take the two radiuses, add them, and subtract them, multiply those two numbers together, and multiply by pi is another way to find the area of the outer black ring.